All right, so let's look at this problem. This is a frame. This is actually something you might see in a structure. There's kind of a horizontal, vertical load applied to one side. Could be wind, could be some other kind of pressure. And then you have a frame section here. It is pinned at C and pinned at A and pinned at B. This is a rigid connection, so no pin there. So we want to find the resultant forces at A, B, and C. So the first thing we want to do is, can I treat the whole structure as a free body? I can, but I would have two unknowns at A and two unknowns at B. That would be 4 total. So I don't have enough equations. I only have 3 equations of equilibrium for a free body, and I have 4 unknowns. So I could get some information, but I think it's going to be easier for us to go ahead and take it apart and look at an element from A to C as one free body and a second element from C to B. And for no particular reason, I'm going to do this first element, C to B, first. So I'll draw a simple free body diagram of that structure. At B, I will assume that I have an X and Y component. And at C is also a pin. Again, I'll assume an X and Y component. And then let's not forget I have my applied force, which is 800 newtons and a length of 2 meters and a length of 2 meters. So for like on the exam question, I may ask you, part A or part B, draw the free body diagram for section BC. So there it would be, free body diagram of BC. So what do we have? Well, we've got 2 plus 2, we have 4 unknowns, and we have 3 equations. So we won't be able to solve for everything here. If I look at the other section, I'll draw it over here, free body diagram from A to C, then what happens? I'll introduce new unknowns, AY, AX, but at C, I've already assumed directions at C, so on this side they are equal and opposite. So now again I have 2 free bodies, 6 equations, and 2, 4, 6 unknowns. And what am I going to do about this distributed load over here?
Calculate the force.
Yeah, what's the resultant force of that distributed load?
2 divided by sine of 60 times.
Right, so I need to find the area of this curve, so I know the height is 200 newtons per meter, and what's this length?
2 divided by sine of 60.
Correct. So I'll just come back up here and say this length is going to be
2.3.
2 divided by sine of 60. What is that?
2.31.
2.31 meters. So that means my force will be 2.31 times 200.
461.
That's what I got. So I'll write this 460. I got 61.88. Let's just say 461.9, and that should be newtons. And it acts in the center, which is half the distance of the 2.31. So up this edge here would be 1.16 meters. 1.16 meters, something like that. Now what are we going to do with it? Are we going to leave it in that form? I think it's going to be easier for us to look at a x and y component of that force. Okay? And let's not forget that this angle was given as 60. So that means that this angle is 60, right? Yeah. That should be all the details I need. So what do I do? It looks a bit tricky. Well, let's just say if I sum moments at A, what I'm going to get? I'll have these two forces, but then I'll have both Cx and Cy contributing. That's one equation, two unknowns. Maybe I should...
Start somewhere else.
Where else could I start?
Point B.
Point B.
Are you just focusing on AC, or?
Well, if I sum moments at B, I'd get another equation in Cx and Cy. I'd have two equations and two unknowns. I could solve it that way. Is there something else I can do? The way I've drawn it here, the answer I think is no. So what could I do to make it easier for me? The challenge is this angle, right? If this were 90 degrees, it'd be a piece of cake, but it's not. So what can I do? Do I have to choose my components in this coordinate system? No, I don't, do I? So what if I redrew this thing and I called this, say, x prime? So I'd still have the same resultant force. That hasn't changed, right? But what if I rotated my so this is Cx prime, Cy prime, and then I come down here. I could leave those alone if I wanted to. So what have I just made easier?
The moment equation?
Yeah, now if I sum moments about A, this component does not create moments. So I can find Cx prime, which I could convert back into my x or y axis.
Is it the only way to do this problem?
No. Well, easily? Probably. If you had plenty of time, you would just write your equations. You'd have two equations and two unknowns, and you'd be done. You could do it that way, because I could sum moments at B and get two equations in Cx and Cy. I could sum moments at A and get two equations in Cx and Cy. Solve them. Once you have them, you can go back and just sum forces and get B and A. So you could do it that way. I just wanted to show you that you're not necessarily locked into standard Cartesian coordinates x, y. You can rotate them any way you like to get the components. You guys see that?
Mm-hmm.
And which way would we like to proceed? Or should we proceed at all? Maybe I'll just stop here and we'll just treat this problem as kind of like a thought problem, a discussion about how to solve such a problem.
Something won't be like this on the test, right?
Oh, I don't think so. Let me draw it one more way, just so you see it. We have the same section, with the same force. And you might find this comforting, you might not. To make this even easier, I could shift not only Cx prime to Cy prime. I go ahead and shift I called that y. I just remembered this should be y, not x. But I can shift these too. Now this one I think is the easiest one to see. You sum moments at A, you get Cx. You sum forces in the x direction, you get Ax. All this is going to tell you is that they're equal and opposite. But you know something now. So when you pass that over to here, you're just going to have to convert these guys back. So anytime things go off our 90-degree angles, just remember that the forces get a little more challenging to keep track of.
We like our right angles.
All right, I'll stop that.